Hi folks, we're going to take a look at number 14 on page 469. So here they ask us to find the k values that make these two planes parallel. So here we see the k value is the coefficient of y, then what k value will make them perpendicular, and then they want us to show whether these planes could ever be coincident. In other words, can they represent the same plane? All right, so let's start with A here. So if I have two planes that are parallel, all right, this sort of stems from the fact that the angle between two planes is the same as the angle between the two normal vectors. So here, two planes that are parallel are going to have an angle of 0 between them, and so will their normal vectors. So in other words, the normal vectors have to be scalar multiples of each other in order to be parallel. Okay, so I just need to determine what k value is going to make these two normal vectors parallel. So I need n1, which is again 4k negative 2, and n2, which is 2, 4, negative 1, to be parallel. All right, so in other words, what value, say, I'm not going to use k here since it's already being used, I need to be able to write n1 as some scalar multiple of n2. Okay, so here we see, if I look at the two x components, 4 would need to be equal to 2p, and so p has to be equal to 2. I notice that it also works for the z values because 2 times negative 1 is equal to negative 2. So now I have a way to solve for k. K needs to be equal to 2 times the y value from the second normal vector. So k needs to be equal to 8, and there's only one answer here. Okay, so if k is equal to 8, these two planes will be parallel because their normal vectors will be parallel. All right, so let's take a look at B. Now here we need them to be perpendicular. So in other words, if the planes are perpendicular, so will their normal vectors be. So in order for two vectors to be perpendicular, their dot product has to be equal to 0. So now I'm going to take the dot product of the two normal vectors for k negative 2. So here I don't anticipate, can't be the same k value as before, since that made them parallel. This needs to be perpendicular. So 4k negative 2, and I'm going to dot that with 2, 4, negative 1, and I'm going to set that equal to 0. And now I can solve this equation for k. So we got 4 times 2 is 8, okay, plus k times 4, so plus 4k. And then here, minus 2 times negative 1 equals 0, so 4k is equal to, so here we have 8 plus 2 is 10, so bring that to the other side, negative 10, so k is going to be equal to negative 10 over 4, or negative 5 halves. All right, so here we see that, again, only one solution when k is negative 5 over 2. The two normal vectors will be perpendicular, hence the planes will be perpendicular. All right, so let's finish off with C here. I'll do it right here. So they ask us, can these planes ever be coincident? So first of all, if they're the same plane, they're parallel, all right? So I'm going to use k equals 8 here because that's the only thing that will make the two normal vectors parallel. So let me write up my equations. 4x plus 8y minus 2z plus 1 equals 0. And then here we have 2x plus 4y minus z plus 4 equals 0. Okay, so in order for these to be the same plane, they would have to reduce to the same basic equation. But here, if I take equation, say I call this 1 and 2, if I take equation 1 and I divide both sides by 4, well, what do I get? Sorry, not by 4, I guess by 2. Sorry about that. Okay, what happens? Well, I'm going to get 2x divide by 2 plus 4y, so that's all good, divide by 2 minus z, but here I'm going to get plus 1/2 equals 0, and this is not the same as plane 2. Okay, so in other words, they can never be coincident. Okay, so while I was able to find a scenario where their normal vectors, where A, B, and C were scalar multiples of each other, I see that the D values are not going to be scalar multiples of each other. All right, so just to recap here, when you're working with the Cartesian equation of a plane, when you're talking about angles between them, when you're talking about perpendicular, when you're talking about parallel, you can work with the normal vectors. All right. To show they're parallel, you have to show that they're scalar multiples of each other, and perpendicular, that the dot product is equal to 0. Okay? And in order for them to be coincident, meaning that same plane, not only do the normal vectors have to have the same multiple, but so do the d values. Okay, that's it for this one.